Hello students, welcome to another video about differentiation. In the previous video, we have discussed the necessity of differentiation, why do we do differentiation, in which situation we are bound to apply this concept, and I have told that when any quantity is changing unevenly or unequally, and in certain circumstances, if we have to make the sum of such quantities, or in certain other applications that sum is to be used, then we have a problem, we should have a problem. Suppose I have already taken two examples. Suppose this is a graph that shows a particle's velocity up to a certain time. Suppose here t is equal to 0 and here t is equal to 10 seconds. In the first graph, it is clearly seen that the particle is traveling with uniform velocity up to 10 seconds. Now, if we are asked that what is the displacement of the particle in these 10 seconds, so we know already that displacement is equal to the product of these two, velocity and time for which it travels. And this is clearly a rectangle, so we can easily find the displacement with the help of the area of this rectangle. And to find that, just we have to multiply this length, that is time axis value, and this breadth, that is velocity axis value. We can clearly take this part as a rectangle. But what about this graph? A particle may travel with non-uniform velocity like this. Suppose let's consider this also starts with time 0. No problem. Time 0. Now, as time, in course of time, as time changes, the velocity at different point of time is different. The value of velocity is different at different point of time. So we do not have a particular value of velocity, for the total time duration, of the particle's traveling, of the particle's journey. But in this case, for the total journey of the particle, everywhere, at every moment, the velocity is same. In this case, the values of velocity are different at different points of time. So what should we do now? In this situation, we cannot take this as a rectangle. So this part is problematic. This part makes the trouble. How can we solve it? How can we resolve this problem? Now, differentiation advises us that let's take an extremely small section of time, extremely small section. And when we divide the total time into such a section which almost reaches the value of 0, then in that extremely minute time interval, the displacement here and the displacement here can be taken as almost same. When you take comparatively longer time interval like this time interval, suppose I am taking this time interval. So what about this part? What about this part? This part is a curvature. This part is not a horizontal flat line like this. Instead, this is a curvature. So this part obstructs me to take this section as a rectangle. This part, since this is not flat, so we cannot take this as a rectangle. But if we make these two sections tremendously close to each other, tremendously close, very close to each other, that means when the time interval almost becomes zero like small, like this, then you cannot make any difference between these two edges. This curvature, when becomes very small, then it is almost out of sight. This curvature is then turns almost flat. It cannot be recognizable. This curve cannot be recognized by us when it is too small. Then that part, that top part can be taken as a flat straight line. When the time becomes extremely small as 0. So when the time interval tends to 0, we can denote it as dt. When time changes, we usually write, traditionally we use delta sign beside t, because this is the change in time. This refers change in time. When you make the change from here to there, or there to there, or there to there, or there to there, that means change in time. So that is del t. But when the change is infinitesimally small, like 0, then delta turns to d. Now when this rectangle, this small part is extremely small, then the top part is almost flat, then you can consider this as a rectangle. Now there is no problem, because the top part, the curvature of the top part cannot be recognized as a curve, so it is almost flat. So you then can take it as a rectangle. You can make its area. How? Now this height and this height is almost same. So if you take this as V, you can also take this one as also V. So this part is V. No, sorry, this part is V and this part is del t. So the area of this extremely negligible rectangle is dA, very small area, and that is equal to V into dt. You can find innumerous this type of rectangles, innumerous very large number of this type of rectangles from here to there, and if you join them, the areas of all those rectangles of such kind of rectangles, then you can make the total displacement, and for that you have to join them up, you have to sum them up, and to sum them there is another method in mathematics which is called integration. Then we can do this. That is another topic. But in this case, this problem can be resolved by using differentiation. So in this case, we can understand by another way in which case we can use differentiation. In certain situations, in certain circumstances, certain factors when change unevenly like this, unevenly, and if we are asked to make the sum of that kind of quantities for a certain range, or to use that kind of sum in certain other applications, then we cannot use the normal process. Then we have to use differentiation. Differentiation is the mathematical tool implement which we can use to break certain quantity which changes very unevenly, and by breaking it into innumerous very large number of such parts which are tremendous small, such small that you cannot make any difference between two consecutive of such parts. And if you can manage to measure the value of each part, then you can make the total sum. Now, in the previous video, I have discussed that how can we break that function? How can we break that quantity? Theoretically, it is okay. We can break the variable factor, and then we can sum such parts up to a certain range to make the total sum. But how can we break that kind of quantity into such small parts which almost tends to zero? That depends on the types of function. What kind of function is this? This curve represent what kind of function? Whether it is a function of logarithm, whether it is a function of sine or cosine or tangent or exponential, what kind of function is this? Depending on that, by using several formulas, you can determine its smallest part, such kind of smallest part. Like its smallest part will be cos x. Its smallest part will be minus sin x. Its smallest part will be this. So if it is known to us that what kind of function the curve is representing, then by using those formulas we can determine its smallest section, this part. And once we can determine each part, then by applying this formula we can calculate the total value, the total sum, which cannot be determined when the function is changing abruptly. Now, there are certain other various types of applications of differentiation in mathematics, in physics. Like if the displacement of a particle is represented by this type of function. Then what will be its velocity? In general, what will be its velocity? So velocity is the rate of change in displacement. So if this is displacement, then if we change it with respect to time, then we can determine its velocity. So this represents the whole function. So when we change this function, that means d of y, change of y, when time changes also. So with respect to the change in time, when we change this function, then we can change also this. And according to the formula of exponential function, we can make this as 3 into 2x minus 6 into 1 plus 0. That means 6x minus 6. This will be its velocity. This represents the position of the particle. Suppose it starts from here, and after a certain time, suppose this is the displacement time graph, and suppose at time 6 seconds, it reaches at a distance of 10 meter. This is 10 meter. So this refers the position at a particular moment of time. So when you apply the value of x here, you can determine its velocity at that particular position and at that particular moment of time. And this refers obviously velocity. When you try to find out acceleration, then you have to differentiate this velocity with respect to time again. If we further differentiate this velocity with respect to time, then obviously it is acceleration, because acceleration is the rate of change in velocity. So time changes, with changing time velocity also changes. That refers acceleration, and that is equal to, we have to again change this. So it shows that the particle travels with a constant acceleration. Suppose this is meter per second square. This always travels with a constant acceleration, means it increases its velocity at a constant rate. That means if you change its position 10 meter or 15 meter or 20 meter or 30 meter, it will not change its acceleration. It will increase its velocity at a fixed rate. So again we can apply this concept of differentiation to measure certain quantities in mathematics which cannot be determined in normal method. Like suppose if we try to measure a quantity of this. Now for this, let me discuss a thing, a certain topic. Suppose this is x-axis, this is y-axis. Here is a point whose coordinate is suppose x1, y1, and there is another point whose coordinate is x2, y2. You have to move from this point to that point. How can you move? Mathematically, how can you move from this point to that point? To reach that point, first you have to move further along x-axis, further a certain distance along x-axis, and then you have to move further along further a certain distance along y-axis. So this can be mentioned as change of the value of x. This is the primary value of x and this is the final value of x. So this refers the change in x and this refers definitely the change in y. Now this part is called slope or gradient, and this term refers the comparable changes. That means when you change the value of x by certain amount, what will be the change in the value of y with respect to that change of value of x. That means you have to move here and then here. So it refers this change in angle, which can be denoted by tan theta, perpendicular by base, that is del y upon del x. Now when this change is tremendously small, this change both of x and y are tremendously small, like they tends to 0. When del x tends to 0, then del refers any amount of change. But when that change tends to 0, like small quantity, then we can change the symbol as d. So from here we can write del y is equal to dy upon dx into del x. This is a formula very much useful for this type of calculation. For this, first we have to assume this as function of x. To its nearest value, which is a perfect square number. To calculate this, first we have to choose a number very close to it, or it is rather to say very closest to it, nearest to it, which is a perfect square number. That means we can do square root of that number. So that is 16, and that can be considered as fx or y. Now if we change the slight value of x, we can write this, and then that will be the new value of this function, and that will be this one. So clearly from this value, this increment is this 0.2 is the increment referred as del x. That means del x is equal to 0.2. How can you measure del y? So del y can be measured by subtracting this one from this one. That means fx plus del x minus fx. So it will be root over 16.2 minus root over 16. So from this equation, if we take root over 16.2 alone at one side, then del y plus root 16 is the value of this. Now previously I have written this one, this relation del y is equal to dy upon dx into del x. So by using this relation, dy dx into del x plus 4. Now what is dy dx? What is y? Y is this function, or here x is termed as 16 √ 16. So y is equal to √x. Y is function of x, and what is the form of that function? That is √x, where x is 16. When x is increased by √2, it will become 16.2. Y is a function of x, and what is the form of that function? √16. That is √x, where x is 16, and when a little bit is increased to that value, it will become 16.2, and that increase is the increase of x, which is del x, that is 0.2 increase. So y is √x, that means it will be x to the power half. So it is an exponential function. We already have discussed that according to the function, the formula is used. So x to the power n, the formula of x to the power n can be used here. N x to the power n minus 1. That means 1 by 2 √x. So here 1 by 2 √x into del x plus 4. That means 1 by 2 √x. √x, that means 4. Into del x. What is del x? 0.2 plus 4. That means when it is cancelled out, this will be 0.1. So 1 upon 40. 1 upon 40 means almost 0.025. So 4.025. So we can calculate the square root of this one, which cannot be performed normally. We can use differentiation to do this. There are other many applications of differentiations in physics. Especially in physics, we can apply various rules of differentiation. Also, there are several uses of differentiation in mathematics. That's all up to this time in this class. In the next videos, we can furthermore discuss about the various types of differentiation of simpler order and higher order. Thank you, students. Bye bye.